Good afternoon. My name is Ian Jeffrey. I am the GIS Remote Sensing Specialist at the Ganaraska Region Conservation Authority. Focusing on LiDAR today in particular, we work with orthoimagery, various other types of data sets, even photogrammetry, which is a different method of acquiring 3D data, but we're going to focus on LiDAR today and community well-being in general. So just an idea of conservation authorities across Ontario. We are one of 36. Ganaraska Conservation Authority is located, our office is located in Port Hope, Ontario, and we're nestled down here kind of in the middle of things. And we take in a bit of the GTA and via Durham, the Clarington portion, and we go basically just west of Brighton. The unique thing about conservation authorities is that our jurisdictional boundaries do not honor political boundaries. They're actually meaningful hydrological units. So watershed type of jurisdictional delineation for the most part. So, you know, the overall goal of conservation authorities being conservation, restoration, development, and management of natural resources at the watershed scale. Really lends itself into the topic of, you know, balancing natural and built assets. So we, on the policy side, we administer the Conservation Authorities Act and sections of the Planning Act from the province of Ontario. And we work with a lot of provincial data. And the provinces, like a lot of us, have been moving slowly but surely towards open data. Their LiDAR coming out now, it's becoming increasingly available. It's openly available now on the Ontario GeoHub site. The point clouds, I believe, are still by order because they're quite large and they'll ship out on hard drive. But anyways, not only has it become more available, the province now has a strategy to acquire LiDAR to try to fill in the holes of areas without it. So it's a very promising development. So that's that. We'll get into the technical good stuff now. The LiDAR system, just really quickly, is essentially laser scanning from a plane. When we're talking about terrestrial LiDAR, there's other forms of LiDAR. There's bathymetric LiDAR. There's ground-based laser scanning, georeference types of LiDAR. But essentially, you're working with a laser scanner out of the plane, GNSS units, so global navigational system like GPS or GLONASS. To orient the plane in the sky, as well as speaking with ground stations or stations on the ground, and then an IMU, which is like a digital gyroscope to understand the pitch and the yaw of the plane in the sky. What you get out of that are point clouds, excuse me, which are large blobs of points, basically in a LAS format. So it's an endless kind of CSV file, if you want to think of it that way, with a header, but. What you get is a blob of points, and these points can be classified each one as ground, building, hydroline, vegetation, different types of vegetation. It depends upon how you set it up, but essentially in our business we're mostly in the modeling of surface water. So we generally use mostly just the ground bare earth models to conduct that sort of business. But in the course of this presentation, I'll show a couple other applications of LiDAR data as well. So when I was talking about interconnecting natural and built assets, LiDAR provides the understanding of how the topography works on any scale that you have the LiDAR. So if you're looking at a municipality, you can have obviously a 3D model of that area. And when you're talking about planning development, you can finally view stuff as one cohesive picture. And the term that's kind of various buzz terms around that, but the idea of geodesign, that you're taking in the natural and built assets into full consideration when developing official plans and other sort of planning initiatives at a municipal level, and specifically within climate change adaptation. It really expands the view and the purview of the planners in terms of where the municipality is going to go in terms of into the future, and anything into the future involves climate change. So you can model various different aspects of the environment within the municipality to increase climate change resilience in a variety of different capacities. So we're talking about flood events, urban tree canopy loss, And then various theoretical planning sort of projections in terms of where the community is headed. So just an example of one community that we were looking to do floodplain mapping in. This is an ortho image showing the community, and the blue polygon showing the main water course, and the orange lines show the area that we're kind of zeroing in on for flood lines. We acquire the LiDAR data, and this showing right here is full feature. So we have trees, buildings, anything that's seen from the sky as a digital service model, DSM. We strip those away to get to a bare earth model. And you can see that there. And then we run hydrologic models to figure out, or to figure out how the water gets into the watercourse, and then hydraulic models to determine how the water behaves within the watercourse. So the hydraulic model will show the flood lines as they're discovered from the data. Like, obviously, you can turn it into contour data, which the engineers love. And then what we can do is take all these things in consideration. We can use them in conjunction with urban flooding aspects, which include municipal infrastructure such as pipes and drainage features. And we come up with a real-time simulation of a flood event within a dense urban setting, within a heritage development setting, which essentially means that if it was planned today, it wouldn't be approved because it would put community in a flood dangerous scenario. So as we can model these, we can work with municipalities in effort to start to mitigate some of these effects, as well as adapt. So I'll speed it up a bit, but essentially this is a buried creek that through the middle, where you not see blue, is buried. Then opens up a bit at the end, and then exits or outputs into Lake Ontario at the south. So with this whole community perspective, we're able to model one watercourse and watch its accumulative effect when under certain flood events on the community. And right off the hop, this goes into emergency response. We can show where fire trucks can get past and how to access different areas based on what the blockages are in terms of inundated roadways and such. And we can actually do velocity mapping as well, because it's not just the depth, it's at the speed at which the water is moving. And it's surprising how shallow water can be if it's moving fast, that can take away a fire truck. So we work very closely with municipalities on sort of planning like that. And obviously the flood lines go into regulatory limits that we work with developers and the public to work around in terms of development to balance the built and the natural assets of a community. This is just another example of the same sort of thing. Stormwater management ponds play a role within flood modeling. But essentially, under any rainfall event, they serve two primary purposes: is to retain flow. It depends on what type of flow, and that's determined by water resource engineering, as well as water quality. It plays a role with water quality. So, but specifically, we're going to focus on the retention of flow, and how we can design these things now that we have this open data and this data that does take in a whole municipality. So typically a stormwater management pond would be designed unto itself. There would be site surveys that would have to tie it into monuments to make sure it was situated correctly. But they generally get designed on their own and then get plugged into a plan and then developed. But in terms of using them into a real-time model to model their effectiveness under flood events is something that's has only been enabled by the advent of these technologies such as LiDAR, 3D modeling, and as well as the various engineering models as well. So we took LiDAR data, the bare earth data. We did a canoe survey with RTK rover. So we filled in points in the middle where the LiDAR did not return any readings because it was terrestrial LiDAR. So over water, you don't get any data back. If you do, it's noise. So we clipped that out. We put in some data that was ground truth by high accuracy GPS LiDAR, RTK survey. And we're able to bring it in and mesh it with the surrounding topography. to create like a real world computer model on how we can plug this into different scenarios and how it behaves. We were published in 2 of the Esri magazines, the American one on the left and the Canadian one on the right for this work. And what you can see is you can extract contours, which really brings it to life for the engineers. And engineers are becoming increasingly fluent with GIS software and stuff like that, but there's still that comfort within seeing contours and doing the math that way sometimes. So we can take an elevation, find out where it spills out of, and then model, sorry, there's the contours again, and then model that over top of a simple ortho image. And we can see where those different elevations are being controlled by the pond and where they would breach the design, the intended design, or the design intents of this feature, and see how it impacts the municipality. And with this, working with the town, there's a little bit of surprise where the water was flowing, but it was natural because we're using as one cohesive picture on how one stormwater pond, protects and serves an entire area, informed by the aerial type topography or LiDAR topography. And then another quick one, urban forestry and LiDAR. So huge climate change considerations with this, but also we're kind of building the baseline of things over the last few years, but since high accuracy LiDAR has been available, and then kind of the uptake into the urban forestry world, we're really starting to just scrape the surface on the possibilities of it. So it's an effective biomass indicator because you can get that 3D quality with it. You can couple it with ortho imagery and just get even more bang for your buck kind of thing. Heat island modeling is a massive concern now with climate change, and that's mainly to do with not with flows, but with water flows, but with heat and the increasing heat in those projections. So managing the canopy, figuring out how to target where trees are being lost and how to target areas that would be best served to plant trees, and then the maturity and all these things of the makeup or the composition of these tree stands throughout the city. So you can do area or individual based modeling, and then better volume predictions, or like that biomass type of able to do is extract and get actual 3D renderings of different tree crowns. And then if you want to, there's also a full waveform LiDAR, which is available by purchase. I'm not aware of any free full waveform, but what that can get into is it returns more information to the sensor than would be a single point telling you just sort of where it is. It can get into the foliage, and you can start to really tease apart species as well. I would love to get my hands on some. I've had some demo stuff, but that's the next step that I would love to take this. But with this stuff, like just LiDAR in general becoming more and more available across Ontario, this is the stuff that that can be done within a GIS environment with remote sensing software as well. One thing that we're playing with now is if there's a theoretical if there's an idea of where one should be, we can actually make one in that mesh. We can fuse it in instead of using that real world RTK data. If I can zoom back to that. We can just slice out an area where it might be, or where it's proposed to be. We can put in the design sort of feature, the non-terrestrial part, and then we can use it to run different scenarios in terms of integrating with our hydraulic modeling as well to see how that would mitigate flooding on the cohesive municipal scale and stuff like that. So that's one thing we're playing with right now, is not just climate change scenarios in the future, not just planning projections, but we can actually show the different scenarios as they're being thought of, which has proved very valuable. We work very closely with municipalities naturally as conservation authorities, so it's a great relationship, and it's been very. I like to see the fact that this LiDAR is becoming a lot more prevalent and easy to use. So with that, thank you for listening.
Excellent. Ian, thank you so much for this. Considering the disaster that took place out west fairly recently, this work that you're doing is absolutely critical, particularly the modeling and prediction work that is important for city policy development, things like creek bank analysis, zoning policies, things like that, and of course, public safety. And I also like the fact that you're looking at change over time, which is super important.